good evening and good morning to all of you. And just to update you on the upcoming ACS Science Talk, please visit our ACS India webpage and register for the upcoming session by Professor Jalal J. Mayer. And we have also updated the past lecture recordings on the ACS Science Talk virtual library. Please visit it, like, subscribe, and share among the scientific community. To begin with the scientific, to update you on the latest research, products, and launches at ACS, we have a monthly newsletter called ACS Insights India. Subscribe today for free. We'll share the link later in the chat box. To begin with the scientific session, it's an honor and pleasure to have Professor Huang with us. He's a professor of material science and engineering at Northwestern University. He received his BS degree in chemical physics from University of Science and Technology of China, PhD in chemistry from University of California, Los Angeles, and became a Miller Fellow at UC Berkeley before joining Northwestern in 2007. Professor Huang enjoys integrating education and research to enhance learning experience for his students and himself. In research, his group uses chemical principles and tools to discover new materials, advance materials processing, and use material innovation for better living. His work has been recognized by awards from the National Science Foundation, the Sloan Foundation, the Society of Manufacturing Engineers, the American Vacuum Society, and the International Aerosol Research Assembly. He is a recipient of Guggenheim Fellowship, the JSPS Fellowship from Japan, and the Humboldt Research Award from Germany. He is a fellow of the American Association for the Advancement of Science AAAS and the founding editor-in-chief of Accounts of Material Research. Now, I would like to invite Professor Huang to deliver his talk. Over to Professor Huang.
Thank you so much. It's my great honor to come here and to share the story about the journal and also about my own research with you. And Accounts of Materials Research is a new journal, a new international partnership journal launched jointly between ACS and Shanghai Tech. And it basically adds to the account portfolio. It's following the success of Accounts of Chemical Research. By the way, in my own research, Accounts of Chemical Research was one of my favorite journal, and has been my favorite journal. And also I personally have published quite a few papers there. So I've always liked the idea about accounts. It's following their editor-in-chief, Professor Cindy Barrow's words, an account article is like a seminar in print. So I hope to introduce a lot of exciting stories in print from material science area to the broad readership. So we publish mainly account type of articles, and account type of articles are basically concise personal review on a topic of materials research, and it is based on previously published results by the same group of authors. And these are very short review articles. They are typically up to 6,000 words, about 8 to 10 figures, okay, usually about 50 references. And we also publish another type of article called viewpoints. And these viewpoint articles are very diverse and flexible. So they can be utilized to talk about, for example, research insights, perspectives, even predictions in a research area that hasn't really been popular yet. And we're also launching a new type of viewpoint article to feature up and coming young investigators, and we call that new PI viewpoints. Okay. And so we hope to use these as a platform, not only to feature the exciting development of materials research, but also make it as a home journal for all materials researchers, and also to feature these material researchers, especially at a critical milestone in their career. Okay, so far we have been able to publish, I think, about 6 issues. Okay, we were launched in last October, and the plan is to publish 12 issues a year. And we've been trying to work really hard to have a fast turnaround. And so far, the average is about a little bit more than 8 weeks from submission to online publication. Okay. And I should also mention that so far we have in the editorial team, we have 3 editors. So other than myself, I was very lucky to be able to recruit Professor Yulin Chen from University of Oxford. He's an expert in condensed matter physics and quantum materials. And we also have Professor Jiaxing Huang from MIT Material Science Department. She's an expert in many things, especially in electrochemical systems and energy materials. Okay, let me show you a few cover images here. Okay, I remember every one of these articles. So for example, in our inaugural issue, we have the two covers, front and the supplementary cover describes chemical catalysis material design for chemical catalysis. And the cover on the back here, this is actually coming from Sir Fraser Stoddart, okay, the Nobel Prize winner and my good friend and colleague. He published an article about the design of porous molecular material. And then we have an article here showing heterostructures along thin nanowires. And here we have articles about rare earth particles for medical imaging and diagnostic applications. And certainly now in the middle one here, we have an article about perovskite, okay? And this front cover here is about organic thin film design for electronic devices. And here is one focused on CVD growth of two-dimensional materials. And here's another cover about two-dimensional materials application in energy storage devices, in particular ultracapacitors with high pseudocapacitance. And here is a pretty special one. This one is outside the typical ACS portfolio. This one is about bulk nanostructure metals that represents a very cool development in metallurgy, where people are making bulk metal materials with nanostructure grains. And in this particular case, the grain distribution has a gradient from surface to bulk that enables really remarkable properties of these metals. And here we have a defect engineering for electrocatalysis. And finally, here's a sneak peek. I don't think this has been released yet. So here's a sneak peek showing a beautiful image. Here's a beautiful image of a dancing droplets enabled by a very clever surface patterning and surface design. Okay, so all the articles are invited by the editorial team through recommendations from our board members, and also sometimes through submitted proposals. So we're always actively on the lookout for new authors and for new topics. If you have an idea about an account or viewpoint, please feel free to send us a proposal. So this is the link right here. Okay, there is a simple template file online that allows you to fill in some information to help you to organize your thought and also help the editorial office to make a quick decision on the proposal. Okay, I think that's that for the journal. Should I switch to my research talk now and take question later? Okay, all right. Let me switch over. Okay, so let me start my research talk today. So I use this title, Materials Innovation for Better Living, because this is actually the title of my research group. Okay, and I would like to use this to advocate some research philosophy and also some thinking that I would like to share with students. Okay, and the subtitle here, Sad New Thoughts in the Pandemic, because most of the topic today are brand new, something that we started to work on just a little bit more than a year ago. Okay, so let me show you why I want to advocate this thought. So as a teacher or as a professor, I'm always trying to think, how do I, well, we oftentimes get questions from students and colleagues about, how do you find the right problem? Or how do you find the right problem behind the problems? And in my own experience, I can't speak for all, but in my own experience, there are some problems that are extremely well known. Okay, you find out the problems by going to seminars and by reading papers, and also by watching out the latest funding trends from various governments. Now, this requires a lot of thinking to distill the real problem that you can solve and behind some of these, I guess, surface descriptions. Now, sometimes some problems can be obtained through specialized connection, maybe privileged access, because not every one of us may know as many friends as others. Oftentimes you will hear that I know a guy who works in this area and he bring up a problem to me. So sometimes examples like that may make you feel like, I can't come up with this problems or solutions because I don't have these access. But I'm going to argue that even for young new researchers, you can come up with very unique and very cool research problems just based on your experience. And here, experience, by saying experience, I mean both your personal life experience as well as your research experience, because oftentimes the best inspiration is really coming out of those. And how do you exactly do that? And I've been a long advocate for curiosity-driven inquiries. Keep up the curiosity, because think deeper. When you see something, ask more questions and try to connect to your own background, and be foolish, okay, and be curious and don't be shy. So practically, I think it will be very beneficial to combine both convergent thinking and divergent thinking together. So in an academic training setting, we have been very good in training students to do this kind of convergent thinking. We present a problem to them and teach them tools and train them to solve it. But if you also start to train students to think outward, okay, brainstorm with them as much as possible, then you can also train them to follow their curiosity and to identify some new connections, identify new problems, and sometimes there will be lots of pleasant surprises. So I'll show you one example, and before that, let me just show you what we typically do in the lab. So what we typically do in the lab is that if you look at the paradigm of material science engineering, these are the 4 key elements. Everything starts from processing. So that's why we decided to work on processing. I am very biased. I was a chemist by training. So we apply chemistry tools and we use chemical principles to advance materials processing. And I think material processing is extremely cool. By the way, materials processing is very diverse. And the reason is that the structural concept in material science is incredibly diverse. It goes across many different length scales, and each different length scale would require a particular set of processing technique. So if you work in processing, you should, and I think you often are, very diverse in your thinking, okay, in your view of the world. So I think I said I was biased because I think processing is very cool and it's very sexy. And if you make an accomplishment, if you advance processing, your impact can be amplified by the whole thought process of material science engineering. Okay, so anything happens here is going to be amplified along the line. So we have been doing a number of works in the past 3-4 years. For example, we're interested in fluidized electrophotolysis and how we can utilize this technique to make catalysts more stable and more fatigue resistant. And we discovered a group of charge transfer solvent that can process carbon nanotubes without any functionalization or additives. And we can make these powders of nanotubes as usable as engineering plastic. And we are also interested in 2-dimensional materials like graphene. This is a photo of paper ball, but that's just a model for a crumpled graphene ball at submicron length scale. That was something that we invented a number of years ago, and we've been having a lot of fun with that. And this is an imaging technique we developed. We call this fluorescence quenching microscopy. And this technique has now been developed to be able to visualize essentially all class of 2D materials using a common fluorescence microscope. And I shall point out that this work was based on an earlier prediction by Professor Sebastian at IIS Bangalore. I think he retired a few years ago. And our work, first published about 11 years ago, happened to be the first experimental proof of what he predicted to be an ultra long quenching distance of graphene. So this is what we have been doing, and we have been having a lot of fun with this. And then, so here's one example about this unconventional thinking. So for graphene-based materials, we have been spending a lot of time to study graphene oxide and its reduced graphene oxide product. So there have been a lot of people utilizing this material all over the world in many applications, and oftentimes you will hear mechanical properties based on mechanical applications based on mechanical property, electrical property, etc. Okay, so now if you get to the basic of this, one day we started to ask our question to ourselves. If you look at these samples in the lab, so this is a aqueous dispersion of graphene oxide. This is just a film. If you cast it out on a substrate, if you reduce it by heating or by adding something like a reducing agent, like a vitamin C, they turn black and then it can flocculate, but you can very easily redisperse them by adding some dispersing agent. So by looking at these, if you see this in front of your eyes, you can ask yourself, perhaps a very cool application can be developed. If you think about the most fundamental property of these materials, these are the properties that you can't even avoid. Okay, so for example, if you want to make very strong graphene sheets or reduced graphene sheets, or electrically very conductive ones, it's challenging. Okay, that requires a lot of refinement. That requires a lot of research. But there are something here just in front of your eyes that is almost impossible to miss, and that is basically the color. So one day we realized that maybe these are great two-dimensional pigment sheets. Can we just use them as a brown to black pigments? Now the question next is that, so where in the world are people going to be interested in black pigment sheets? So here we go. An example of connecting to experience. I mean, again, experience can be just your observation as well. It doesn't have to be something you actually personally experience through. So we realized after some brainstorming that there's one area that black pigments can really make a difference. This is hair dyes, okay? So, well, here's a photo showing this is basically bleached blonde hair. And you can certainly chemically dye it and turn it black, but if you just coat them with this graphene-based ink, they turn very black, and the color looks very natural, very close to natural black hair. And now these are graphene-based sheets. We're now utilizing the color, but don't forget that they are still graphene. Okay, they may not be extremely conductive, but they are conductive enough to make some differences when they are used as hair dyes. So here's one quick demonstration. So if you have chemically processed hair, basically this bundle here was the bleached hair processed by commercial chemical hair dye. The right one is graphene hair dye. So if you rub them with plastic sheets, you're going to electrostatically charge them up. So this is what you normally expect, right? The hair will fly up. But the graphene hair dye is anti-static. So you're not going to have these annoying fly away problem, okay? Now, the other one is a little bit subtle, but graphene is also a pretty good heat conductor. So if you heat up the chemically dyed hair and also graphene dyed hair, and you do notice that the graphene coating helps the hair to heat up and cool down more rapidly. So this should be more useful in terms of heat dissipation. And because usually for heat dissipation, people would try to improve the air circulation or maybe just bundle hair up to avoid heat accumulation. So these are pretty fun. There are many other aspects of the story, but in short, we realized that this was a very good material solution to a actually extremely difficult chemical problem. Okay, now it not only makes a black hair dye, but it introduces new functions. But the ultimate lesson here is that this is one of those stories that the problem was identified by observing ordinary people's life experience. Okay, I think many of you would know someone that used hair dyes. And we wanted to, and we also got a lot of inspirations by talking to people to understand what is the problem behind the current hair dye ideas or strategies. So we hope this can benefit ordinary people very soon, right? So again, this emphasized the idea that there are many worthy research problems out there that you as a new researcher or as a young student or as a new researcher in any given area, okay, regardless your career stage, you can actually identify these problems and make some worthy discoveries. So under this guiding philosophy, we have been having a lot of fun in the lab in the past many years. So these are some of my group photos taken, extracted from the last few years. So we're very happy. We got this in a sunny day. This is, by the way, taken on Northwestern campus. We are right next to Lake Michigan. That's one of the biggest lake in the world. And either in a very brutal cold winter, we still are very happy, okay? And for the hair dye work, we actually got two people here, Dr. Murad Kadir and Dr. Pankar, and they were working together and try to advance the hair dye coating. And we've been busy, and we had been very happy. And as you know, then here comes 2020. And I was trying to find ways to express my feelings, but I think this particular meme here summarizes it really well. Okay, the crushing despair of everything from the past year. So our life has been tossed around, and a lot of things have changed. And you know, like many of you initially, especially starting from last January, everyone was affected, right? So some of my group members shown in this photo right here. For example, we have two brilliant students. This is Qie Zhang and this is Ziyi Kong. They were actually both from Wuhan. And in fact, one of them just returned to Wuhan right before the pandemic hits. So we had a lot of anxieties as well. And we have a lot of frustrations as well. And how do we cope with that? So I apologize that this is gonna sound like a yoga, okay? But eventually I found peace and I found power in studying. And in particular, I decided to purchase this textbook. So this is a set of textbook called The Principles of Virology. And this is a brilliantly written textbook. It's written by a team of authors led by Jane Flint. Now, I do recommend that everyone, if you can get a hold of these textbook, this was the 4th edition, but it doesn't matter which one you have. I do recommend everybody can read just the first maybe 2 chapters in both volumes, and they are incredibly powerful. Okay, once you read those, I think you will get a lot more confident, and you can see, I guess you can understand our challenges, and you can see perhaps some way out much better. So I'll just share with you a few sort of thoughts after reading the textbook. The first thing is that I was no longer really afraid of the virus, because viruses is everywhere. They completely overwhelm anything else we know, okay, in the biosphere. So here is some information from the textbook. For example, in terms of the biomass wise, right, the viruses, bacteria viruses alone is already like about 1,000 times heavier than all the elephants combined. And if you connect all these virus particles together, okay, it can reach to many exoplanets, okay, 200 million light years away. And also in our cells, right, we are full of viruses, okay? The average human body contains about this many cells, but about 1,000 times more virus particles. And in fact, if you dig into, do a little bit more reading, you will realize that we are what we are because of viruses. And viruses played some enabling effect, enabling contribution to shape the evolution of modern human beings. So without viruses, we're not going to be this intelligent animal on Earth. So, okay, we have been living with them forever. Now, the second one is that, for those viruses that can make you sick, how afraid should you be? And again, this is after reading the textbook, I realized that, my goodness, you don't have to be so scared about this. So I found out that I spent some time yesterday to find out this a screenshot from a computer game. Maybe some of you have played this game before, but I just found this perfect to illustrate what I learned from reading the textbook. So if these are viruses, especially these viruses related to respiratory diseases, if you are worried about them attacking human being, so for example, here's one little human being right here. So there are actually many layers of defense mechanisms. So you should really be thankful for that. because these viruses, they must travel outside human body and they must go through physical space in the material world. So for example, oftentimes in the news or when people talk about how we deal with this, we oftentimes focus on immunological intervention or biological intervention. So for example, what happens in our human body, or for example, we're waiting for a magic cure, a medicine, a medical treatment, or a vaccine, okay? But those are really at the final lines of defense. Now, immunological intervention and biological interventions are really the most sophisticated one. They are highly accurate, they're very sophisticated, very intelligent, but they can be easily outnumbered. Now, before that, before the viruses reach the last lines of defense, there are many layers of environmental and physical intervention ways that you should apply. Now, these are not as intelligent, but they are extremely effective. And in fact, in most infectious diseases, these factors will actually inactivate or remove the overwhelming majorities of virus particles before they reach you. So with that, we became a lot more confident. So I started to read more about this, and we also dig into medical literature, and quickly our extracurricular activities ended up becoming what we have spent most of our time in the past years. So a few highlight here is that we started to pay attention to this after the news about Wuhan lockdown broke out. And I started initial discussion with a few friends and colleagues, and eventually was able to convince a very brave student to join me to study together. We were study buddies at that time, and we were able to write up a document recording our thoughts, hypotheses, and some research ideas. And after we wrote that, we sent it to the US National Science Foundation, who were actually advocating them to release a call for proposal for people to address the COVID problems from the non-biological side of science and engineering. We eventually submitted the proposal, and after a few rejections, finally received the award notice rapidly. And then we started to prepare for the experiment, and we were able to find a group of biomedical and clinical experts to join us, and finally published the call in last April, about this time. And that was published in ACS Nano. So that's this paper right here. Now, let me just start by thanking some of these people. So there are only 2 people from Northwestern. So this was my fearless graduate student, Jiaxing Huang. We have the same last name, but we're not really related. So without her, it was impossible for me to really complete the self-study. Okay, so she was remarkably efficient in reading textbooks and searching medical literature to confirm our hypothesis. I need to thank a second former group member. This is Professor Hua Li, currently in Shanghai. She was a former member of my research group. So when I called her up and said that, I wish we can talk to some medical doctors, clinicians who have frontline experience with COVID. And amazingly, I mean, she didn't know most of these people in a photo, but she was able to find her friends and friends and friends through 3 or 4 layers later. In very short period of time, she was able to connect us with all these wonderful individuals right here, right? So let me just highlight a few of them. So for example, this is Professor Min Li. She's the director of a COVID testing task force in a hospital in Shanghai. And she offers tremendous insight about testing and about, and also did extensive revision of our manuscript. And this is Professor Ruilang Wan. She was the director of an intense care unit in Shanghai. When we talked to her, she was actually just finishing up her tour to Wuhan. She led a medical team to work directly with COVID patient and try to recover and strengthen the ICU effort in Wuhan. And she was under quarantine at that time because she was just returning. And she spent a lot of time to share her observations and to share her insight. And for example, she was the one that first brought up the idea that we should really start to pay attention to the sustainable materials used in PPEs because they are used in massive quantities, okay? And this is another wonderful medical doctor, Dr. Xin Zhen. She was a Northwestern alumni, and she was actually the head of the COVID task force of her hospital in Wuhan, and she's started working. I mean, when we got a hold of her, it's usually after midnight in China when she was just off her shift. Okay, and this is a Professor Hui Wang. She's public health in Shanghai Jiao Tong University. So she was able to lead a public health campaign. For example, her first open public health seminar attracted about let's see, that's 5 million views. Okay, and accumulatively, they were able to be distributed and reached over 100 million people in less than a month. Okay, these are all remarkable individuals, and we were so fortunate to have a chance to work with them and to learn from them. So let me just say that these are all my Wonder Women. Okay, so we're tremendously grateful to them. All right, so after, what do we have in the paper? What's the purpose of that particular paper? So the purpose of the paper is to educate ourselves and our peers and share with our students the basics and share some hypotheses. And we also present some needs and research ideas to advocate people for action, okay, especially those who are not working in biological side of science engineering. So here are two physical pictures about viruses and respiratory droplets. The first one is that from a structure property point of view, that's the classical material science thinking. If you think about structure property of, from this angle, the sole purpose of virus particles is to infect and reproduce. That is the property they need. So in order to generate those properties, structurally wise, they must be metastable, and they are actually quite delicate. Now, the good news is that if you want to disrupt this process, if any part of the virus particle, the protein, the membrane, any part of the structure is disrupted, then they will be malfunction. They won't be able to accomplish their sole purpose, which is to infect and reproduce. So that means there are many, many ways to inactivate them. This becomes now a problem of delivery. How do you deliver external stress effectively to the virus particles? Now, the second physical picture, which is very important, and I found out that has been oftentimes misunderstood, is that when people release respiratory viruses, we are never releasing the viruses as individual naked particle, individual naked particles, okay? Because you can try to spit on your phone screen and look at what happens after your respiratory fluid dries, right? There are lots of other junks. And in fact, viruses are oftentimes a minority component in the droplets or in the final dried nuclei. In the final dry nuclei, the virus particles are embedded and surrounded and protected by all these other things. So this is extremely important, because now if you want to design any sanitization or inactivation mechanism, you must consider the surrounding respiratory mass. For example, any mechanism that relies on molecular contact with the viruses would likely be ineffective, because most of the time you're not even contacting the virus, right? You basically are contacting this big chunk of composite particles that are at micron sizes, that with little particles embedded inside, okay? So this also explains a lot of misinformation about masks, right? You oftentimes hear people talking about how no mask is useful because there's no mask that can stop 100 nanometer size particles, but that is not true, because we're not really filtering individual naked particles. We are trying to block droplets and the dry nuclei, which are much, much larger and typically in the micron range. So that's two important physical pictures. The other one is the overall big picture of infectious diseases and the general public health strategy. And knowing this can help you to identify where you would like to work on. So for any infectious diseases, they have three key elements. The first one is the source, and then the possible transmission pathways, and finally, the most susceptible group of targets. So source pathways and targets. Now, it's extremely important to be able to identify the source pathway and the target, and then develop mitigation strategies. So for respiratory diseases, if you look at this cartoon right here, it is very obvious and intuitive to learn that, well, if you want to manage this, if you want to block the transmission, the most effective way, I mean, all the methods should address at least one of all of the three of the elements, but the most effective way is really try to manage the source Okay, so for example, if you want to put on a mask, you can, if you put on a mask on the individuals here, you offer personal protection, but here you actually offer much greater degree of protection overall in the bigger picture. And the key reason here is that we're dealing with drastically different concentration of aerosol droplets, or even just regular droplets, because at the source, you are dealing with orders of magnitude higher numbers of and volume in comparison to individuals here, where you're trying to block like 1 or 2 particles from coming to you. So this is the biggest difference between masks on every individual as a target and a mask on those individuals as potential source. So we decided that we should focus our effort in managing the source. Okay, so that became our main effort for the past few years. For the past year, okay. So we're also putting a lot of hypotheses and new ideas in this perspective article. And we worked with the Global Communication Office in Northwestern to re-roll the article in a more general, accessible form. This is our outreach effort. So this is a long list. Actually, this is still incomplete, but you're welcome to take a look at that. And there is a more comprehensive list over there. Okay. So after all these, we hope this helps to inspire some people to think seriously about the problems. And we also realize that, you know, it's great that you are advocating people to do something, but it would be even greater if you actually just go ahead and start some of the ideas yourself. So we decided to do this. And by the way, you see the transition from those photos taken at various places outside to eventually a photo taking right inside the lab. And we decided to pick up some of the ideas and start to actually go work on those ourselves. And this became a typical day in my research lab. Okay, 4 of them, including 5 of us, including myself, we were able to qualify for essential research status at Northwestern. So that allowed us to come to the lab during campus closure. At that time, when the university was closed, you are not really allowed to come to research lab or your office. Even if you can't, there's going to be no logistic support, right? Because everything is supposed to be shut down. But if you're essential researchers working in COVID-related work, you can come. So these 4 really brave individuals. So I should again thank them first. This is graduate student Jiaxing Huang. This is a research associate Murad Kadir. This is postdoc Zilong Yu and postdoc Han Park. So they could have just sit at home and wait it out, okay? Just read papers and do some light reading work. But they all decided that they want a better way to use their energy and time. So they all volunteered, right? And there are actually more people who want to volunteer to come, but we were limited by the capacity that we can handle during a pandemic, because we have to institute very strict social distancing rules. And this was just a brief moment where we come together to take a photo, okay? So they decided that they would come and drop whatever they were doing and start brand new research directions. So I'm gonna have time to talk about maybe 2 research directions right here, 2 projects briefly. The first one is about chemical modulation of respiratory droplets. The second one is aerosol capture by indoor environmental surfaces. The first one was mainly led by Jiaxing Huang and Han Park. The second one was led by Murad and Zilong. Okay, we have 2 additional projects that I won't have time to talk about today. But for example, even for our undergraduate students who had to stay home remotely, they were able to actually do some in-house experiment, okay, based on supplies they can purchase through Amazon. We also shipped her some of the equipment in the lab, so she was able to complete a good chunk of in-house, at-home garage research that became the foundation of her undergraduate senior project. So this is the ongoing. We have another line of project trying to retrofit stainless steel with a self-sanitizing surface layer. So let me introduce the ideas and challenges in the first one, which is on-mask chemical modulation of respiratory droplets. So the main idea or the goal here is that we would like to develop a mask concept that emphasizes their role as PHE. So you all know that mask is a very critical component in PPE, personal protection equipment. But I will argue that masks are even more important as PHE, public health equipment. Okay, because what we want to do here is that we would like this mask layer to chemically modulate the escaped droplets. Now, we are not thinking about blocking all the droplets, because by doing so, you're making this mask very difficult to breathe through. You don't want to suffocate people. So we're thinking about that even with very loose textiles and loose fabrics, if you let the droplet pass, but now you chemically modulate them, maybe that would be a way to help to make the sources less infectious, okay? And this will become a tool for better protecting others, okay? So the main technical challenge here is that, number one is the baseline consideration. You must avoid inhalation hazard. So anything you do to modify the textile should not contain volatile chemicals and should not contain ultrafine particles, because otherwise they become an inhalation hazard, no matter how strongly you anchor them. So the second is that we would like to load anti-pathogen agents. So there are some broad spectrum agents that's well known in literature, such as acid or metal copper ions, for example. There are also many other organic species. So for these anti-pathogen agents, they should not be inhaled in, but they should readily release, okay, and release and dissolve in the escape outgoing droplets. So the idea is that when they carry some of these anti-pathogen agents, as the droplet dries up, the concentration will shoot up because the concentration will scale to the third power of the diameter. So it will be greatly concentrated to well past the threshold for deactivating viruses. So the other challenge is that this is easy to think about, but how do you actually characterize that? So we need to find a way to count, to image the escape droplets. We also need a way to quantify the degree of modification, which is practically the concentration of these modifying agent in the outgoing droplets. Okay, it's easy to think, but how do you actually do this? But fortunately, Haiyue and Han, they were able to come up with some really clever designs. So this is the overall design. We used a air sprayer to simulate the respiratory droplets generated during sneezing and coughing, though this is a high velocity droplets and large volume droplets as well. They can, by large volume means that they also carry the highest viral load, okay? So the idea is that if we have a non-woven fabric here, if we coat it with a modifying layer, then hopefully the droplets, when they pass through this layer, they will become doped with these anti-pathogen molecules or species. And when they land on a detector screen, we're thinking that, well, if we have a colorimetric detector screen that will change color when the droplet is modified, then maybe we can just count them, okay? So that's, again, easy to think about, but practically turns out to be quite challenging to do. So for the chemically modifying layer, we ended up choosing polyaniline coated medical gauze. So medical gauze is quite common, but polyaniline, the reason to choose that is that polyaniline has a reversible doping dedoping chemistry based on acid and base reaction. You can load acid very easily by just soaking a textile in a mineral acid solution, and they can be dissolved away if you put that in water or in basic conditions. And the same thing can happen with metal cations such as copper. So for the colorimetric detector screen, initially I was thinking that, oh, this is super easy. Let's go get some pH paper, okay? Because if polyaniline loaded with acid is used as the modifying layer, when the droplet pass through the screen, it will become acidic. It will change color on the pH paper. That's a piece of cake, okay? So I did propose these to my two students, and then that ended up wasting their 3 weeks of time because, well, long story, but basically didn't work. So I shut up and just start to play a supporting role. And very interestingly, they found out later on that you can actually use polyaniline itself as the colorimetric detector screen, and I'll show you why. So this is the synthesis. And polyaniline is one of the easiest conducting polymer to synthesize. And basically, this is an in situ grown method. You take a medical gauze, you soak it in a growing solution, and as the polymer grows through polymerization, and you will have a very strong layer growing on the fibers of this medical gauze layer. And then you can purify, wash it, and try to remove some of the non-specifically adsorbed large debris. And then you can redope it with acid and metal salt. So we chose phosphoric acid because it is fast dissolving and it's non-volatile, okay? And it doesn't dry up to become extremely corrosive like sulfuric acid. So for the colorimetric detector screen, Haiyue and Huang come up with this brilliant interfacial polymerization technique where they pretty much float a piece of smooth plastic sheets on the surface of the polymerizing reaction. And this gives you a very uniform film as shown in this photo right here. And if you if you peel part of that and look at it under AFM, it's actually an incredibly uniform film that's just about 100 nanometers thick. Now, in order to use it as a colorimetric detector screen, it has to be optically uniform under optical microscope. So here, this large image here is a transmission mode of optical microscopy image. It shows a beautifully uniform blue color. So this is a necessity. If you have a lot of textures and uneven distribution in the background, it will mess up your image processing. So how can we quantitatively count and also determine the degree of modification? And this can be done amazingly with just an ordinary optical microscope, okay, with reflectance and transmission mode. So here's a subtle difference between the two imaging mode. For the transmission mode, you see through the sample. So that's why you see the color of the film, which is blue. Now, for the reflective mode, you can see all the droplets because they contain respiratory mass. So in our model droplets, we add in polymers and salt based on standardized recipe. There are these model respiratory fluid out there. So when this droplet landed on this detector screen, they would dry up and the respiratory mass, the dried mass would deposit, they will change the surface roughness of the film. So under reflective mode, they will scatter light more, so they will be less reflective, so they will appear as dark spots. So here is a reflectance mode image. Now, but when you look at them through transmission mode, if they are not as modified by acid, they are unable to change the color of the blue polyaniline film because they cannot dope it. So everything, and also because they are fairly thin, so under transmission mode, there's really not much feature, right? This is a transmission mode of unmodified droplet. You just spray them directly on the film. So there's not much in it. But now if you have acid-modified droplet, they can dope the polyaniline film here and turn it from blue to green. So that's why under reflectance mode, you still see all the droplets. But now when you turn on transmission mode, only those green enough spot will become visible. Green enough means that they have been modified by sufficient amount of acid, because we understand that the escape droplet, each individual one of them will have different acid concentration. Some are modified, some are not modified at all. And this turns out to be a way to tell which particular droplets are actually being modified. So by combining these two and through a long story of imaging processing algorithm that another MS student developed, Yihan Liu developed, and with Haiyue, then we were able to quantify the degree of acid modification for each individual droplet. And you can now also do statistics for the percentage of modified droplets. So to make a long story short, here is the result. Oh, by the way, this is for acid, but for copper concentration, we developed another imaging technique based on fluorometric imaging. That's specifically for copper. I'll skip that part. But let's take a look at the results. So these diagrams represent a statistical analysis for many tens of thousand droplets. Okay, so so the x-axis here is basically the radius of the droplets. Each dot represents a droplet. The y-axis is the degree of modification, which is pretty much which is equivalent to pH or acid concentration. So we define a threshold, the dashed line here, the red dashed line here. So the threshold corresponds to droplets with a pH, modified droplet with a pH about 2.3. So anything above the line is considered modified, because anything above the line would have a pH value smaller than 2.3, which, by the way, that is a much higher value than needed to inactivate most viruses. Okay, so the control here is unmodified medical gouts, a plain medical gout. You cough through it, okay? And you see that there's very little droplets that's been modified. These are probably just processing and imaging errors. But then if you use a medical gout modified with polyaniline, and you can start to see a lot more droplets in this modified zone. And if you use a little bit denser fiber mat, in this case, it's a lint-free wipe. This is basically a very common clean room wipe that people use in the lab. And you can see that now you can greatly increase the fraction of the droplets that's been modified. So here's the statistics. The medical gouts has just about 11% of fiber density. If you try to breathe through a medical gouts, it's very easy. If you try to measure the pressure drop, it's barely measurable. And for the clean room wipe, it has about 19% fiber density, and the pressure drop is even smaller than a common medical mask. But now if you look at the percentage of droplets that's been modified by number and by volume. Well, by volume here is more important because the viral load is scaled with the volume of the droplets. So with the wipe, you can actually modify over 80% of the droplets by volume. So this means that this general idea, it's a proof of concept for this general idea. Even non-woven fabrics are quite effective to chemically modify these droplets. So there are a lot more work needs to be done. For example, we were not able to do any clinical tests on this. There are various barriers for us to do that. But I hope people all over the world can maybe pick up this idea. By the way, this is free idea out there. So polyaniline is just a model system. I am certain there are many other material systems that might work even better. And even if you have to use polyanilines, at least in the proof of concepts we demonstrated, they seem to be a feasible option. So I encourage everyone to give it a try. So we were also oftentimes asked about where do you see this being utilized? So we think that this will be most useful in places where you have high number of infected people. So this will be places like a patient wards, nursing homes, long-term care facilities, or some of these like temporary shelter hospitals for sorting COVID patients. Okay, so in fact, in the SOPs of these shelter hospitals, you will see that they actually do distribute medical masks for patients because they also want to reduce the viral concentration within their indoor environment to better protect other patients, as well as the medical workers inside. So another area this might be useful is to enhance those masks with Evolve. So my students from India once told me that the public health policy over there discourages people from wearing these evolved masks in public, because these kind of masks protects you really well, but it offers no protection to people around you. The reason is that there's a very clever valve here. So when you exhale, it basically just leaks all the exhaled air out. Okay, the exhaled air is unfiltered. So but this design is very clever because it decouples inhalation and exhalation. So you actually don't have to worry too much about inhalation risk here. So you can simply put a modifying apparatus or add on to the exhaled valve, and that will help to sanitize the outgoing droplets. Okay, so again, these are all open ideas now, so I welcome everyone to take a look at these. So in the remaining time, I'd like to just, do I still have time? Okay, let me see.
Yeah.
Okay, all right, so this has just a few slides. This addresses another issue for indoor work. So imagine the future of work, and just right now and post-COVID. So in an indoor environment, every person is constantly releasing aerosol droplets. If you talk, if you breathe, you are releasing droplets. And these droplets, there's one problem. Small aerosol droplets are very elastic. They bounce off surfaces. They don't stick to surface really well. So when that happens, it leads to an accumulation of airborne droplets. And each droplets here potentially in the pandemic potentially is a source of infection. So if you can remove these aerosol droplets, then you effectively eliminate them from the chain of transmission. So here's just an image to show you how how elastic they are. So when you have droplets colliding on a surface, so this is the observation geometry. You have a slide, and we are shooting a string of aerosol droplets. We are observing the slide from the back. And you can see that there are a lot of blinking dots. These are basically droplets colliding on a surface and quickly jumped away. There's barely any droplets sticking to the surface. But now if you modify the surface with a formulation containing hydrophilic polymer as well as some combination of surfactants, which by the way, this combination is really a cosmetic ingredient that people use to treat your hair. So you see where this idea is coming from. Okay, it was from the hair dye team at that time was suspended. Okay, and they repurpose their work, refocus their energy to do this. So after you apply for that coating, and you can see now the droplets, a lot more droplets can be fixed on the surface, right? All these things are droplets. They get trapped, and then they will dry up. Okay, so well, with this observation, we go ahead and start to do a more definitive study, which is turns out to be very primitive. Basically, you shoot these aerosol drains with model respiratory fluid at a treated surface and watch the weight gain. So we can see that without any modification, this is the mass increase of an untreated glass slide. Glass slide is already quite well in capturing these droplets because glass slides are more hydrophilic than many other surfaces. But with this layer treatment, you can increase the capture efficiency drastically. And we figure out the optimized thickness. So this is demonstrated in this experiment where we pass a string of high concentration aerosol through a plastic tube. And for uncoated tube, you can see that after just a few seconds, if you shine a laser beam at the exit, you can start to see strong scattering. That means the droplets have escaped the tube just after a few seconds. But if you have a coated tube at the same concentration of aerosol, you can see that you almost eliminate them because even after over a minute, there's a very faint laser scattering light right here. So that means you practically trapped most of the aerosols inside the tube. So then we go ahead and try this. We did a field test. Basically, all the essential workers participated in this experiment, including myself. Okay, we wear a face shield, or we speak to a plexiglass screen coated with this. And we put a few collector slides here, okay, to map out, count escaped droplets. And now here, it's both large fluid droplets and also small aerosol droplets. We also, by the way, have to develop another optical imaging method to do this, okay? But basically you see here that if you don't have the coating, and if you look at the collector here, this is a little silicon wafer here, and if you image the escaped droplets, the number count is here. Now, the number of droplets emitted by people are greatly different, okay? Different people, depending on how you read, how you sing, what language you were using, the droplets are very different. But for every person, after you apply the coating, you can greatly reduce the level of escaped droplets, almost to the baseline level. So the baseline is basically a collector put it outside the screen. There shouldn't be any direct droplet deposition. So this almost indicates that you can use this coating to greatly suppress aerosol bouncing and aerosol diffusion. They are much better in capturing aerosol and limiting the spread scope, the range of the spread. Okay, so now if you look at the indoor environment again, and the coating can be formulated to coat almost any surface, plastic, glass, wood, metal, concrete, textile, and you can even load pigments or load antiviral agents in there. Okay, so we hope this can be utilized to improve the quality of work, to make future of the work and make reopening quicker and more feasible and safer. Okay, so this is finally a promising note, right? I really need to thank these group of very passionate and talented students, and also special thank to all my program managers who bravely let us either support our work or let us repurpose the existing grant to do COVID-related work. So again, the take-home message here for all the students: stay foolish, stay curious, and I hope you all stay well. Okay, thank you very much.